So we'll discuss few more things about integration and a bit of practice. We'll look to wind up calculus now. Okay, so hope all of you had a good test yesterday, and make sure you go through the questions once again in the next couple of days, and any doubts among the questions, do let me know. We will discuss them. Okay, so in the previous previous lecture, we had discussed one important sort of technique of integration by substitution. And we had discussed this type of substitution, that when the integration involves a composite function f of gx multiplied by derivative of the inner function in the composite function, then we can substitute directly gx as a new variable, and therefore so this and this can be substituted in the integration. That becomes this, which is where I is nothing but the antiderivative of f. So this is the final aspect of indefinite integration with substitution that we had discussed. Okay, so we will do a bit of practice related to this, and we'll also understand how to incorporate this when there is when there are limits or we're doing definite integration. Okay, so try this example out, people. So remember, in indefinite integration, you can always check your answer yourself by differentiating the antiderivative. Yes, very good. That's correct. Okay, so let's go through the steps of this again. Okay, so what we can see is that in the denominator, we have a square root term with 1 plus x square inside. And you know that derivative of 1 plus x square is 2x. Okay. So you can use this. So we can do a substitution. Take 1 plus x square as z. So dz by dx is 2x. So you can see that dz is 2x dx. Okay. So basically, we can substitute x dx, which is the numerator, as 1 by 2 times dz. So that constant term half doesn't really matter. So this and this can be substituted. So the integration becomes which can then be solved like this by the formula. So very good. Those of you who sent me the answer is correct. Okay. So square root of 1 plus x square plus is the integration of x upon square root of 1 plus x square. Now on this only we have to put the limits for the second part. Okay. So we can just express it this way. Leave out the constant because anyway it cancels out. So the upper limit is square root of 2 and the lower limit is square root of 1. So the answer is root 2 minus 1 or approximately 0.41. Okay, so let's now look at some more types of substitutions. Okay. Now, last time we had seen that if we have this integration, then we can substitute, or we can directly use this as the antiderivative, because we know so we basically know that differentiation of tan inverse x is equal to 1 upon 1 plus x square. However, this above integration, instead of memorizing it, you can also understand it as another example of substitution. So this is the direct method that we just know that tan inverse x is the antiderivative of 1 upon 1 plus x square. So this is one way that we just remember this factually. Or another way is that we use a substitution. And this time we use a trigonometric substitution. That x is equal to tan theta. Now, what is the logic of this substitution? Okay. Logic is the identity that 1 plus tan square theta is equal to sec square theta. Okay. And the differentiation of tan theta is equal to sec square theta. So this identity makes the denominator very simple. 1 plus x square just becomes sec square. And in the numerator, we will have differentiation of tan theta, which is directly sec square. So that is the reason why we make this substitution. This is the logic behind making this substitution. Okay. So just make a quick run through up to here and we will discuss how to get the above result by substitution. So one is we directly remember this. Because we know that this is the antiderivative of 1 upon 1 plus x square. Or the second method of doing an integration like this one is to use a trigonometric substitution. Now in the trigonometric substitution, we will substitute x as tan theta. And the logic of doing that substitution is this, that because we know as an identity that 1 plus tan square theta is sec square theta. And we also know that the derivative of tan theta is sec square theta. So this statement below, this is the logic of making the above substitution. So just understand it up to this point, then we will incorporate the substitution and see how it works out to be the same integration as above. Or it gives us the antiderivative in the same way.
Sir, if I was to substitute sec square theta, then it would be then I would get a new equation 1 plus tan square theta is equal to d tan theta by d theta, right? And if I were to integrate, then so tan cube theta would be equal to 3.
Okay, so I'm sure now all of you must have worked out how to make use of this substitution. So once we have this, okay, so for example, in the above integration, this one, let's say this is the integration I'm trying to do. I just substitute x as tan theta. So that means the whole denominator becomes sec square theta. And the numerator, which is dx, for that I can see that differentiation with respect to x of tan theta is differentiation. It's okay, so it's sec square theta d theta by dx is equal to 1. So this and this can be substituted in the integration. So the integration becomes, the numerator dx just becomes sec square theta d theta, and the denominator, which is 1 plus x square, is sec square theta. So that is d theta, which is okay. Now what is theta? If x is tan theta, that means theta is tan inverse of x. So as you can see, the antiderivative of this comes out to be tan inverse x plus c. Okay. So this integration, which was originally, this becomes like this. So this is the substitution method of doing it. Okay. Now this substitution method will now become a more general method for us. It will help us not only in this specific integral dx upon 1 plus x square, it will help us in a whole, you can say, family of integrations or a variety of functions whose antiderivative can be calculated using this as a trick. Okay. So this is our first example of what we call a trigonometric substitution. Yes. Very good, Mansi. That's correct. We could have alternately used the identity between cosec theta and cot theta, and therefore we could have substituted x as cot theta also. Okay. So alternately, we can also use for this integration. We can also substitute x as cot theta. So dx becomes minus cosec square theta d theta, because the differentiation of cot theta is minus cosec square theta. So the integration becomes which is the same thing as tan inverse x. Yes. Okay. Actually, there's a different way of proving this. Okay. And that is this, that cot inverse x is equal to minus of cot inverse x is equal to theta, let's say. Okay. That means so it's a little bit tricky. You can say that these two are equivalent. Suppose this is the case. Okay. That means we can say that we can make use of this identity basically, that cot theta is tan of pi by 2 minus theta. And include the constant in this. So suppose this is x. Or basically it like this, that tan x is cot of pi by 2 minus x. Okay. So therefore, so suppose this is theta. So that means x is equal to this moment. Anyway, so there is a way of proving this trigonometrically. I'll just come back to that. Okay, so if tan inverse x is equal to theta, so x is equal to tan theta, which is the same thing as cot of pi by 2 minus theta. So now you have this pod of pi by 2 minus theta is equal to x, which means that pi by 2 minus theta is pod inverse x. So theta is pi by 2 minus pod inverse x. Okay. So that basically shows that tan inverse x is the same thing as pi by 2 minus pod inverse x. So this is the proof of this experiment. So when we have got this term, now remember this is a generic constant. Okay. So therefore minus pod inverse x plus c can be written as tan inverse x minus pi by 2 plus c. Now this thing can be combined and written as one constant. So that's how it becomes this. So it's a little bit like complicated to show that these two things are equivalent. That ultimately tan inverse x plus c is equivalent to minus of cot inverse x plus c. But that's how you can show the same thing. Okay. So actually, this is a very interesting point over here, that what we can write as an antiderivative as tan inverse x plus c can also be written as minus of cot inverse x plus c. They are equivalent to each other. You can just add that as an additional point over here. Okay, so hope this point is clear now, Mansi, that if we use cot for the substitution, it comes to an equivalent answer. It is
Yes,
not
sir.
that, so it's a little bit tricky that tan inverse x is not equal to minus cot inverse x. Tan inverse x is actually equal to pi by 2 minus cot inverse x. Okay, but because we have the constant of integration, and that is a generic term or an indefinite term, so we can incorporate that over here. Right? So you might say that why I have not written pi by 2 minus cot inverse x on the right hand side here, but that is because that pi by 2 is adjusted in this constant. You can say that this constant is a different one than this one because pi by 2 is adjusted, but both of them are indefinite constants. So ultimately, the constant of integration. Okay. Anyhow, so now the whole point is that we can make use of this kind of substitution for doing a whole range of integrations, not just specifically this one. So the first one we'll see is that, so trigonometric substitutions. So trigonometric substitutions are done on the basis of identities. Okay. So the first type is using the identity that 1 plus tan square theta is equal to sec square theta, or we can always use this one, and the fact that differentiation of tan theta is equal to sec square theta. So okay, so for example, like last time we had seen this variation, that if we have this, still we can use this identity but in a slightly modified manner. Okay, so here a is any constant, so it's just a numerical constant. So here the substitution we'll use is that x is equal to a tan theta instead of tan theta. Okay, so that the denominator becomes this. So it becomes a square sec square theta, and the numerator becomes this. Dx can be written as a sec square theta d theta. So this term Okay, and this term can be substituted in the integration. Okay, you can say that this denominator and this can be substituted. So the above integration becomes this. The numerator simply becomes a sec square theta d theta, and the denominator just becomes a square sec square theta. So it's 1 by a coming outside. Okay. So 1 by a to theta plus c. Now we substitute theta as, now we can see that tan theta was x by a. So theta is tan inverse x by a. So this becomes 1 upon a tan inverse of x by a plus c. Okay. So that is what the integration becomes. The antiderivative of the above function, it becomes this. Okay, but another thing we'll see is that this is useful for not only this particular function, which is based on the function 1 upon 1 plus x square. Just the 1 is replaced with a square. So a bit of a modification. X is substituted as a tan theta instead of tan theta. Okay. But it can also be used in a variety of integrations of a certain pattern. That's what we'll look at next. Okay. So these trigonometric substitutions, each of them that we are going to discuss, they are involving a certain trick. Okay, and here the trick that they're involving is basically making use of this identity that 1 plus tan square is equal to sec square, and the derivative of tan is also sec square. Okay, so let's see another example. Suppose the same thing I had was this. I had the integration like this. Okay, now we can see in this integration, I cannot use the earlier type of substitution that we had done today. The first example we had done today was there was an x in the numerator. Here, there is no x in the numerator. So there's not going to be much point substituting 4 plus x square as z. Because what are we going to do with about dz? Because dz will be equal to x dx or 2x dx. So it's not going to help so much. However, I can still make use of the identity. Okay. So I can write this as 4 plus x square can be written as 2 square plus x square. And we can use the identity that a square plus a square tan square theta is equal to make use of this. So what I should do here is I should substitute. So that will get rid of that square root in the denominator and make it integrable. It will make it simple enough. So we'll substitute x or x as 2 tan theta. So then the denominator, which is this, will become square root of 4 plus 4 tan square theta. So there's a 2 that comes outside instead of 4. So the denominator becomes this. And further, so dx can be substituted as 2 sec square theta. So these two things can be substituted in the integration. So my integration becomes, in the numerator, substitute dx as 2 sec square theta d theta. Right? And the denominator, substitute the whole thing, that is square root of 4 plus x square as 2 sec theta. So now we are left with this, which we know is ln sec theta plus tan theta plus c. Okay. Now the resubstitution step is a little bit complicated, so I'll come to that. So this needs to be resubstituted. In the resubstitution, keep in mind that what was our what was our x? X was equal to 2 tan theta. So that means tan theta is x by 2. So that means what is sec theta? It is square root of 1 plus tan square theta. So it is square root of 1 plus x square by 4. Or it is square root of 4 plus x square to the half. Okay. So sec theta will have to be substituted as this, and tan theta will have to be substituted as this. So the integration finally, so the resubstitution step is a bit lengthy. It becomes ln of sec theta, which is 1 by 2 square root of 4 plus x square, plus tan theta, which is x by 2 plus c. Now another very critical step here. We can take the half common. Okay. So the whole thing divided by 2. And then we can use the property of log, that ln a by b is ln a minus ln b. Come like this. Okay. Using this property, that and after having done that, now you can understand that this is a constant term. So therefore c minus ln 2 is also basically a constant of integration. So ultimately we can express the indefinite integration as natural log of square root of 4 plus x square plus x plus a constant. It doesn't matter whether we write the constant as c prime or c. It is basically an indefinite constant. So it's a bit of a lengthy operation, but this is what we come up with finally. And at a later stage, you can just verify this by seeing that what you get when you differentiate this term. So this differentiation will itself be a bit of a lengthy thing. Okay. But if you differentiate it and verify it, you'll see that it will come out to give you what we had started with, which was 1 upon square root of 4 plus x square. Okay. So I'll just leave you to go through the steps of this carefully. We'll practice few more questions of this type. Then we'll identify that how we make that decision that we should use this substitution. In this case, the substitution was x is a tan theta, because in the denominator we have a term which is of the type a square plus x square. It's not directly a square plus x square. It's a square plus x square to some power. Okay. So using that, we make the decision that this is the substitution that has to be made. So just take a minute to go through this, all the steps and all. Okay. Do the verification later also, it's fine. Okay, when you're reviewing today's lecture notes. But we will now generalize this method. Okay, so this is a particular type of situation where we can use this type of substitution, which makes use of the identity that 1 plus tan square is x square.
Sir?
Yes.
In a sum like this, is it really necessary? Like you said, we generalize where we need to use the identity method. Right here, we don't really require it, do we?
Sorry, come again, beta. We don't?
That we'll generalize where we use the trigonometric substitution method.
Yes.
Right here, we don't need it really, right? We can just do it simply too.
How can we do it directly, beta? Tell me, without the trigonometric identity. Like,
Uh, okay, one second.
we can't do the integration directly, no, beta, because inside the square root there's a quadratic term, no? There's x square term. You understanding, no?
Yes, sir.
And see, with the dx in the numerator, there is no linear term like x, no? So there's no point substituting 4 plus x square as z. See what will happen if I substitute 4 plus x square as z. I'll just run into trouble because dz by dx is 2x. So dx in the numerator has to be substituted as what? dz by 2x. And that's a big problem now because this means that x is equal to what? It is square root of z minus 4. So that just means it's, so that leaves me nowhere. No? Then the integration becomes dz upon square root of z minus 4 into this other term which is z. So this is not going to help me. No? Understood the point, no, beta?
Right, sir.
Okay, so that is why now we have, whereas, so the thing is that, you know, if we try this effort over here, we come to a dead end. This is our dead end. This is not going to work out further. Okay. Whereas if we notice that, okay, there is a term like a square plus x square. So why not make use of this identity? Wherever there's a term of a square plus x square, this kind of term, okay, we can always use this identity that x is equal, I mean, we can always use this substitution and make use of this, that tan square theta plus 1 is sec square. Okay, so that will reduce that. Okay. So that is a thing that we look that inside the square root there's a square plus x square kind of term which we can easily simplify using this. Understood the point now?
Yes, sir.
Okay, sir. Yeah, so that's the difference, Bhavika. Again, that same point that when we had the integration of this thing, suppose we had x dx upon square root of 1 plus x square. Here also we can use the tan theta method, but it's unnecessary because there is x in the numerator now. Okay, so this substitution is going to work out nicely. Okay, so I can substitute 1 plus x square as z. Okay, but in this one there is no x in the numerator. So hope this is clear, Bhavika.
Yes, sir.
Yeah. Okay. So again, it's a bit of a matter of practice and experience of doing a lot of integrations that you learn to identify that where what substitution we can use. Okay. So whatever practice we are doing here in basic calculus, you will do 5 times that amount of practice in advanced calculus in maths later. So you'll get used to all these things, but few of the types which are important for us in solving physics problems, I'm going to take you through them so that in future when we are using them in physics, things are smooth for you. There's no difficulty in understanding the steps. Exactly. That's correct, Bhavika. Okay. So now to generalize this particular method, we can see that if we have any integration of the type e square plus x square to some kind of power, then we can use, obviously n should not be 1, because if n is 1 we can directly integrate it, but in general any other power, like suppose n is half or n is minus half, like the previous one we did, or n equal to minus 1, any of these, then we can use the substitution x is equal to a tan theta. Okay. So a square plus x square becomes a square sec square theta, and dx becomes a sec square theta. So even for example, if we have something like this, square root of 1 plus x square, we can make use of this. Substitute x as tan theta in this case. Okay. So dx becomes sec square theta d theta. So the integration becomes and then there's a longer way to proceed for this. We'll discuss about that later.
Sir, this sum can be done without substituting also, no?
How? Tell me, madam.
Sir, integration of root 1 plus integration of x square.
Kaise? This root, the term inside the square root is 1 plus x square. No? So how we can separate them out, you tell me?
Yes, sir, yes.
Okay. So we have to do a substitution. Okay, so now let's also look at an example of something like this with limits.
Sir, can you scroll up one? I just have to see that.
Sorry?
Can you scroll up, please?
Yeah. So I'm not showing the further process over here because this is solved further using a more complex identity.
Okay, sir.
Okay, now I also want to show how we can use this kind of substitution with definite integrals. Okay. So suppose I have this. This kind of thing. X tending to infinity is the upper limit. X equal to 0 is the lower limit. Okay. So here we will start with the substitution. Now you'll notice the a square term. Now we'll think of 2 plus x square as a square plus x square. So a is root 2. Okay. So that's why we should substitute x as root 2 times some tan theta. So theta is our dummy variable. So therefore, 2 plus x squared just becomes 2 sec square theta, and the numerator becomes root 2 sec square theta d theta. So the integration now becomes but with the limits. Okay. So x equal to 0 to x tending to infinity. Okay. Now the thing is, this limit x equal to 0 will convert it to a limit of theta. Okay. And x tending to infinity will also convert it to a limit of theta, because the variable of integration. Okay, so here what we are doing is we're converting the limits. Limits are converted from x equal to 0 to x tending to infinity to theta tending to something to theta tending to something, or theta equal to something. So how is that conversion done? That conversion is done using the same relationship between x and theta. Okay. So this conversion is done using the relation x is equal to root 2 tan theta. So you can see that theta is tan inverse of x by root 2. So therefore you can see that at x equal to 0, theta is equal to tan inverse 0, which is 0. Okay. And at x tending to infinity, theta is equal to tan inverse infinity, which is pi by 2. I mean tending to pi by 2. Tan pi by 2 actually is not defined, but so this is more like theta is tending to pi by 2. So this becomes therefore, so we substitute this over here. So the lower limit becomes theta equal to 0. The upper limit becomes theta tending to pi by 2. So we have 1 by root 2 theta, on which we'll put the limits theta equal to 0 to theta equal to pi by 2. So this will become 1 by root 2 times the upper limit minus the lower limit. So our final answer is pi by 2 root 2, or 3.14. This kind of. So even this has a significance, and we'll discuss about that. This is actually the area under a certain curve. Okay, and it's a very interesting thing that we are looking at the area going over an infinite domain, 0 to infinity, but the area is finite. Okay. So this is one of the interesting aspects of area under a curve, an application of integration. There are certain types of curves which are such that even if you take the the domain over which we are calculating the area to be an infinite domain, the area comes out to be a finite domain, a finite value. Anyhow, so this is how we incorporate the limits. Okay. Yes, Bhavika, we will be doing more examples where we will convert the limits also using the substitution.
Okay, sir. Thank you.
Okay, so anyhow, hope this example is clear. Now, the interesting thing that this example shows is that we have just shown by this example that integration of, for example, this function 1 upon 2 plus x square from x equal to 0 to x tending to infinity is ultimately pi by 2 root 2. So what is the meaning of this? Let's understand that geometrically. So if you were to plot this function y is equal to fx, where that function fx is which one now? It is this function 1 upon 2 plus x square. Then the area under the curve from a to b is nothing but the integration of that function from a to b. This is nothing but the area under fx from x equal to a to x equal to b. So let's check out what that is in this particular case. So in this particular case, you can see the function is such that if we take the value of y at x equal to 0, it's equal to half 1 by 2. So let's say this is 0.5 or half. And then if x is increasing, what is happening to y? Y is decreasing, such that as x tends to infinity, y tends to 0. So y is equal to 2 plus x square. You can see that x tending to infinity, y tends to 0. Or on the other hand, x tending to minus infinity also, y tends to 0. It's a function that has this kind of a graph. If you do its whole analysis by derivative and all that, you will see that it has only one local maxima point, which is at x equal to 0. So that becomes a global maxima point. So now the area that we are talking about, which is this thing, x equal to 0 to x tending to infinity. That is interestingly this whole area going up to infinity. So this area is equal to this, which will also show you another interesting thing, that if I take the area on the negative side, it will also be the same. So this will also show you another thing, that if I were to take the limits from x tending to minus infinity to x tending to infinity. Yes, Janvi, I'm just coming to you. Just a moment. It will actually give me double of this. Okay, which you can do by putting the limits in the indefinite integration above. Yes, Janvi, what's your question?
So, but the area is actually not finite, correct? Because pi and root 2 go on.
See, the interesting thing here is that this function drops very rapidly. Okay, so even though x is tending to infinity, here the height of the function's graph starts to tend to 0 more rapidly. So that's why the area becomes finite. So we'll see in mathematics, there are certain graphs which give us a finite area for an infinite domain. Exponential is another example, e raised power minus x. If you remember, we have done this question earlier with me, integration of e raised power minus x from 0 to infinity. That also gives a finite answer. It gives an answer of 1. Okay. Whereas there are certain graphs that don't do that. Okay. Like if you integrate 1 by x from 0 to infinity, you will get an ln infinity kind of term, which is not a bounded quantity. It's not a finite quantity. So it depends on how rapidly the graph is decreasing.
Okay, sir.
You understanding, Janvi? So
Yeah, but
this
pi
is,
is so
sorry?
pi will go on and on, right? So
But pi is not an infinite number, right? It's an irrational number, okay, but it's not an infinite number. You're understanding the difference between the two things, no? For example, we can say definitely pi is less than 4, no?
Yes, sir.
What the point is? And definitely we can say root 2 in the denominator is greater than, let's say, 1.4. Okay. So you can say the area is definitely less than a certain limit. So it's not unbounded, it's not infinite.
Yes, sir. Yes, sir. Correct.
You following my point now? Okay. So that is the interesting thing about this, okay, that the area is finite. Even though the upper limit taken is x tending to infinity. That is the interesting aspect about this. Anyway, so like that's, yes, the nature of mathematics. Like you can come up with very interesting things about functions by using calculus alone.
Sir, what is tan inverse of minus infinity?
Tan inverse of minus infinity is like this. See, remember the tan graph, no? The only difference that you have to remember is that when we talk about the graph of y is equal to tan x, okay, then we take the domain as infinite domain, excluding the points of the type pi by 2. Okay, so it's like there's a discontinuity in your graph every time there is a odd multiple of pi by 2. Okay, but when we take the inverse trigonometric function, we take only the primary domain. So it's the, it has to be only between what is happening between minus pi by 2 and plus pi by 2. So we will not take this sort of point which is beyond pi by 2. Okay. So when we take the inverse trigonometric function, so this is y is equal to tan x graph. But when we take the inverse trigonometric function, y is equal to tan inverse x, we will see that we take the reverse of only one cycle of this. So it's like this. So as x tends to infinity, y tends to pi by 2, and as x tends to minus infinity, y tends to minus pi by 2. Okay.
Okay,
So
sir.
tan inverse of minus pi by 2 is equal to, sorry, tan inverse of minus infinity is minus pi by 2. Yeah, Srijita, you have a question, beta?
Sir, why do we consider just one cycle?
Why did we consider?
Only one cycle in the inverse function.
Because see, what happens is, if one is a very simple technical reason that any function cannot have multiple values of y for the same value of x. Understanding, no? So if I
Yes.
consider, so we cannot define the inverse function in that way. So that's why whether you take a function like y is equal to sine inverse x, okay, or y is equal to cos inverse x, or for that matter y is equal to tan inverse x. Okay, if you see the reverse of this, x is equal to sine y. Now if you look at this here, y is the independent variable, x is the dependent variable. So we can have multiple values of y which point to the same value of x. But here we can't have that because x is the independent variable and y is the dependent variable. So we cannot take values of x which are such that they give us multiple values of y. So for example, so that is why we define it in such a way that sine inverse of 1 is only pi by 2. It's not pi by 2, 2 and pi plus pi by 2.
Yes, sir.
Okay, so that is why the sine inverse functions graph will just look like this. For example, when x is equal to 1, y is equal to pi by 2. Yes. Sort of. Kind of. Okay. Now let's come to our second type of trigonometric substitution. Okay. So that is using this basic one, that this one we know is sine inverse x plus c. Okay. So because we know that differentiation of sine inverse x is how much? It is 1 upon square root 1 minus x square. Okay. But also it can be done by substitution. Okay. So we use identity that 1 minus sine square theta is equal to cos square theta. Okay. And differentiation of sine theta is equal to cos theta. Okay. So we use this identity and this relationship. So we are doing this by substitution. We will use this method, that x will be substituted in this case as sine theta. Okay. So when we differentiate both sides of this equation, we'll get cos theta d theta by dx is equal to 1. Or actually, I should write that in reverse order. Okay. So dx in the numerator should be substituted as cos theta d theta. And square root of 1 minus x square so this in the denominator is substituted as this. So the integration becomes dx is substituted as cos theta d theta. Denominator is cos theta. And theta is nothing but sine inverse x, because x was sine theta. So the integration becomes this. Just as you know, if you're doing the reverse of this, how would you prove this? We prove it this way, that y is equal to sine inverse x. That means sine y is equal to x. So realize that actually, you know, it's like two sides of the same coin. This is the inverse process of what we're doing here. Okay, so just make sure you understood the steps in this. Let me know if there's any doubt. Yeah, Dhruv, I'm just going through your question. So why do we substitute x as a tan theta only? Because we have a function which we are integrating, which has a term of a square plus x square to some power. So we want to make use of the identity that a square plus a square tan square theta is equal to a square sec square theta. That's why we substitute x as a tan theta. Substituting as some other trigonometric variable will not make use of that identity. So when we substitute x as a tan theta, when we want to make use of the identity of tan theta, that 1 plus tan square is equal to sec square. Is it clear?
Yes, sir. Sir, but we could have used that 1 plus cot square theta is equal to
Those are interchangeable. But the only thing is when you use cot na, there is the extra minus sign, because differentiation of cot is minus cosec square. So unnecessarily there's a complication of an extra minus sign. So it's better to use the tan theta one. You're understanding my point?
Yes, sir. Okay, sir. Got it.
Okay. So like that, we'll see here that when we substitute x as related to sine theta, we could have also substituted cos theta instead, because there's the same relation between cos and sine, that 1 minus cos square is sine square, 1 minus sine square is cos square. But the derivative of cos theta involves a minus sign. So to avoid that extra complication of minus sign, we generally substitute in terms of sine. Okay, so let's look at the generalization of this now. So any integration of this type, okay, other than, of course, n equal to 1, which is a direct substitute. I mean, it's a direct integration. Okay, we can substitute x as e sine theta. So e square minus x square becomes okay, and substitute dx okay. So for example, suppose we have this integration. So here what we can substitute x as 2 sine theta. So the denominator just becomes 4 cos square theta. Okay. And in the numerator, this becomes this. So substitute these two, and the integration becomes now once again, see here we have substituted x as 2 sine theta. Okay, so that means theta is sine inverse x by 2. So if you think about it, theta is this angle of some triangle where hypotenuse is to, perpendicular is to hypotenuse is x is to 2. So what will be the base? Be square root of hypotenuse square minus perpendicular square. So it will be square root of 4 minus x square. So we can substitute sec theta as hypotenuse upon base. So that is 2 upon square root of 4 minus x square, and tan theta as perpendicular upon base. So x upon. Okay. So this becomes 1 by 2 ln. Now sec theta will be substituted as this, and tan theta will be substituted as this. And that becomes our answer. So now this is a very critical step. This from x equal to 2 sine theta, how we got that sec theta should be this and tan theta should be this. Okay. So I'll just make this a little bit larger. So we can. So this term that we have got, this basically tells us that sine theta is x by 2. The perpendicular is x, then the hypotenuse is equal to 2. So the base and from this now we've got this and we've got this.
Sir,
Yes.
sir, what if we had e to the power a square plus x square?
That wouldn't really help, because the thing is, see, we could substitute. Let me think. Wait. E raised power x a square plus x square
Yes.
dx. No? So here if we substitute x as a tan theta, for example, so dx becomes a sec square theta. So this doesn't really help, because this just, it doesn't really help. So it doesn't give us any direct way of solving this. Okay, maybe a further substitution can be done and it can be solved, or this might be a non-integrable function. I'm not sure. Okay, but this
Yes,
method
sir.
will not directly help us, at least. Okay. So that is why the
Yes.
general form I told you now, where you use this identity, is where you have e square plus x square to some power. Okay.
Yes, sir.
Bhavika, you're asking integration of ln sec theta plus tan theta, or you're talking about differentiation of ln sec theta plus tan theta? Okay, integration of any ln based term is a little bit more complicated. It involves another method called integration by parts. Okay, so that we'll be coming to later in advanced calculus. Okay, so that's why you would have noticed we haven't done any integrations with ln function, right? Okay, let's do another practice example, this time with limits. Okay, try this out.
So that is 9, no?
Yeah, it's integration of square root of 9 minus x square dx with the limits x equal to 0 to x equal to 3. Okay, so let me check out the answers you people have got. Okay, so what's the first thing? We will do a substitution here, right? So we will substitute x as 3 sine theta. You can also alternately you can also substitute x as 3 cos theta. Okay. And interesting how you will get the same answer finally from both. But anyway, so doing this substitution, square root of 9 minus x square will become 3 cos theta. Okay. But also dx will become 3 cos theta d theta. And here what would happen? Here square root of 9 minus x square would have become 3 sine theta. Okay, and dx would have become minus 3 sine theta d theta. So here the integral would have become minus 9 sine square theta d theta. Okay. Here the integral will become 9 cos square theta d theta from x equal to 0. So x equal to 0 involves theta equal to how much? And x equal to theta involves, 3 involves theta equal to how much? So let's understand that. So we have x is equal to 3 sine theta. So theta is sine inverse x by 3. Okay. So from this we can see x equal to 0 involves theta equal to sine inverse 0. That is 0. Okay. And x equal to 3 implies theta equals to sine inverse 1, which is pi by 2. So this goes from 0 to pi by 2. Something similar here also, don't we? So here x equal to 0 will mean that theta is equal to pi by 2. And here x equal to 3 means theta is equal to 0. Now remember the trick we had discussed, that integration of cos square theta is integration of 1 plus cos 2 theta by 2. So that is make use of that integration, because so this is the answer you should have got, 9 pi by 4. And proceeding this way also you'll get the same. But here you'll have to substitute sine square theta as 1 minus cos 2 theta by 2 to proceed. Yes, very good, Mansi. That's correct. If we are expressing it as an indefinite function properly, then we have to express it that way. 9 by 2 into sine inverse x by 3 plus that term.
Yes, sir.
And then you can put the limits on x also. But see, if we are putting the limits anyway, then sometimes it is more convenient to do it this way, that convert the limits from x to theta rather than get the answer in terms of x and then put the limits. Okay, so we should also know that if we are doing this as an indefinite integration, we're just doing this, then using the same substitution, this would become square root of 9. So the c will come later. This is d theta. Okay. So this would be theta plus sine 2 theta by 2 plus c like this. Okay. So now here we would substitute theta as sine inverse x by 3. Okay. From this. And we would substitute sine 2 theta as 2 sine theta cos theta, where cos theta would become so square root of 1 minus x square by 9. Or okay, so sine 2 theta by 2, which is sine theta cos theta, would become x by 3 into square root of 9 minus x square by 3. So that would be x square root of 9 minus x square by 9. So this term would become like this. Sine inverse x by 3 plus this term, x into square root of 9 minus x square by 9 plus c. So if I was doing this as an indefinite integration, this would be my answer. As a definite integration, I could bring it to this answer and then substitute the limits of x, or I could just do it this way, that I could write the limits in terms of theta. So you'll see here, I have another option. Instead of converting the limits, I can bring the answer to the form of x first, like I've done below, and then substitute the limits of x from x equal to 0 to x equal to 3. That will give me the same result, or I can do as I've done above. Okay, so for the indefinite integration or antiderivative, you do this. This would be the antiderivative. Okay, so these kind of integrations, things can get little little bit complicated. Okay. We will not come across a whole lot of them in physics, just now and then a few here, few there. So you should just keep these two basic trigonometric substitutions in mind. Okay. So in general, you can say that these two are equivalent to 4, because wherever we substitute x as a tan theta, we could have also substituted as a cot theta, or wherever we are substituting x as a sin theta, we can also substitute it as a cos theta. But we will in general avoid those two because we don't want the extra minus sign to unnecessarily complicate things. So there are a few more substitutions like this in advanced calculus also. As I told you, like indefinite integration is a very, very lengthy topic in advanced calculus. You'll probably be doing the same amount of work in indefinite integration as we have done in differentiation and integration put together so far in advanced calculus. Okay. But the thing is that we will be coming to in class 12th, whereas a lot of our class 11th physics will involve some integrations, and those will be covered by what we have done in the basic calculus syllabus here. So you need not worry about integration as far as the application in physics is concerned. Okay. There is a lot more to be done in the subject on its own, but as far as what we need in physics to progress further is concerned, for the entire 11-12 syllabus of physics, if you have your basic calculus notes written down properly and from time to time you do a quick revision of these terms, you should not have any difficulty with the steps of calculus in any physics problem. Okay, so just to wind up today's class, I want to show you one interesting aspect. Okay. Compare these three things. Integration of dx by x from x equal to 0 to x tending to infinity with integration of e raised power minus x from x equal to 0 to x tending to infinity with this thing e raised power x tending to minus infinity to x equal to 0. Just work out these three integrations, compare the results that you get, and try to analyze them in terms of graph. I'll bring you to that in a moment. Okay. First, just try out the integrations yourself and see whether you get any finite results or not. We've already seen the 1 upon 1 plus x squared from 0 to infinity. But that also we can compare alongside. Okay, so you will realize that with the first integral, you have a huge problem because neither ln 0 is defined, okay, nor ln infinity is a finite quantity. If you remember the ln graph, it's like this now. So x tends to infinity, ln x tends to infinity, and x tends to 0, ln x tends to minus infinity. So therefore, 0 to infinity, so is not defined itself because ln 0 is not defined. So effectively what that shows you is that if you look at the graph of the function y is equal to 1 by x, it's a rectangular hyperbola, what we call in maths. That's function that like this. So this kind of area cannot be defined only. It's an undefined area. Okay. But for example, if I said from x equal to 1 to x equal to 2, then that's fine. That is, so that is ln 2 minus ln 1, which is ln 2, which is approximately 0.69. So that's fine. Because now you're looking at a finite portion of this curve. So looking at this area. This area is very well defined. But this kind of area cannot be defined here. Whereas take the second one, or the third one, and you see you get a defined value of area, you get a finite defined area, even though you're taking x over an infinite range. Okay, so that is because the exponential function has that property that its curvature is much sharper. So if I look at the function e raised power x, e raised power minus x, in only this part of the domain from 0 to infinity. So on this side it will be like this, okay, but I'm just looking at this part now. So interestingly, this area will again be a defined value of area, like we had seen in that tan inverse graph earlier. This is e raised power minus x with a minus sign. You don't need to write the constant of integration as we had seen earlier. So this is minus of e raised power minus infinity, minus of minus e raised power 0. This is the upper limit, this is the lower limit. So this is this, okay. This is one. So this area is this. And if you compare this with the other one that we discussed, So this was the B part. We discussed about the C part. Extending to minus infinity to x equal to 0. You see, this is the graph of y is equal to e raised power x. It's just the mirror image of this graph. So now we're talking about this area. It should come out to be the same, no, as this area. So integration of e raised power x is e raised power x. So the limits are minus infinity to 1. So e raised power 0 minus of e raised power minus infinity. That is 1 minus 1 upon e raised power infinity. That is. So this area over here is the same as this area over here. But replace this exponential graph with a 1 by x type of graph, or what we call a hyperbolic graph, it becomes an unbounded area. So that is the point I was trying to explain to you, that integration gives us this interesting result that on the face of it, we might draw the graphs by very similar type of curves. They are dropping like that and tending to x to 0 as x tends to infinity or whatever. But there is a difference in their curvature, which is why in one case we get a bounded area, in one case we get an unbounded area. Okay, people, so with that we complete today's session. Srijita, if you want to calculate the integration of a mod function, then we have to express the mod function that way. Okay, so for example, if we are doing integration of 1 minus x square, or let's say we are doing integration of, let's say, very simple. Let's say we are doing mod x from x equal to minus 1 to x equal to 1. So we have to understand that what we are doing is we are calculating the area under a graph, but which graph? Mod x. So we have to understand that y equal to mod x itself is defined in this way, that it is y equal to minus x for x less than 0. It's equal to 0. Yes, Janvi?
So it's not related to this after this.
It's not, sorry?
Sir, I have a doubt, but it's not related to the current.
Yeah, what is it, Pita?
Sir, if we integrate a function in a certain interval, we will get the area of the graph for that interval. But if we integrate for a point, what will we get?
We get 0, no? So if you integrate any function from a to a, we'll get the value of the indefinite function at a minus the same value, no? So it will be 0 by definition.
Yes, sir.
Or you can think of it like this, that you are integrating from a to b and let b tend to a. So when b tends to a, the area that you are integrating, it has, like, you know, the x, the change in x for it is tending to 0, no? So the area will tend to 0.
Sir, I was trying to explain it actually in terms of the integral. Matlab, sir, in an interval, we're actually adding all the values of the integral, right? That is what we say is the area of the graph.
Yeah. So your delta x is 0, no? Your delta x is tending to 0, no? If your upper limit is equal to your lower limit. Got it, no?
So then for a point on the graph, what is it?
It's nothing, no? It's 0, because there is no area enclosed, no? At a point. It's only for an interval that you have an area.
Sir, in terms of the integral.
See, this graph only, suppose I was integrating it from 1 to 1. So what it means actually, 1 is this particular point, no? And the second limit is also 1 only. So do I have any area enclosed by the graph? I don't know.
Yes, sir.
Okay, so in this case, what I'm doing is, like, if you think of this now, this is your graph of y is equal to mod x, right? So that's why you can see it is the line y equal to minus x, which is this one, and it is the line y equal to x in the positive order. So that's why this function has to be split like this. Okay, so Srijita, this is clear so far?
Yes, sir.
So this integral, in terms of geometry, what we are doing is we are calculating this area, which you can see that this area should come to be area of this triangle plus this triangle. So half of 1 into 1 plus half of 1 into 1. So it should come out to be 2.
Sir, I
Okay.
understood the graph part. I was asking about the analytic.
Now how we'll do this now? So now see, we'll have to use this definition of the function. Okay. So this definition of the function means that, see, now I'm taking limit from -1 to 1. Whereas when x is less than 0, the definition of the function is something different. And when x is greater than 0, the definition of the function is something different. So we'll have to split the limits from -1 to 0. But -1 to 0, what is x? Mod x, it is minus x. And then 0 to 1, what is mod x? It's x. Understood? Huh?
Yes, sir.
Now proceed and put the limits, you will get the same answer. Just a
Sir,
moment,
but
I'll
do we need to make 3 cases?
you don't need to, the 0 is just 1 point now. So actually you can just take less than 0 and greater than 0. Following now?
Yes, sir.
Okay. So okay, people, so we will pick up this mod kind of term in the next class again. But in the meantime, you can try out one question yourself. You can take an example to further understand this point. See the difference between doing integration of sin x from 0 to 2 pi and the integration of mod sin x from 0 to 2 pi. Okay. So interpret both these results, both in terms of graph as well as splitting the domain, like I've done over here. Okay. So first, okay, so try this out as a later homework exercise. We'll discuss this in the next class. We'll have to conclude here today because time is up.
Sir, I had a question that in the graphs of e raised to power x and e raised to minus x, why didn't you count area in first quadrant for first one and second for second one?
Sorry, why didn't I?
Sir, could you please scroll up, then I'll tell you.
Yeah. Yeah, tell me.
So like in e raised to power minus x, why didn't you count area for like second quadrant, and then in e raised to power x, why didn't you count it in for first quadrant area?
Because that would give me an unbounded value. So there's no point in doing that. Understanding now? So if I were to do minus infinity to infinity, both of these would give me infinite values, not finite values.
Okay, sir. Okay, got it.
That's what. So the point is, this part of the area is finite. In the first one, 0 to infinity is finite, but minus infinity to 0 would not be finite. And likewise, in the second one, minus infinity to 0, the area is finite, but 0 to infinity, the area is becoming unbounded. Got it now?
Yes, sir.
Okay. Okay, so people will conclude here today, but now see, we are done with all the essential concepts of integration. Next lecture, we will discuss some questions and some doubts and all in integration, but you can wind up integration now. I'll be sending you a worksheet, but also now wind up your your module exercises, okay, of calculus. Next chapter we'll be doing is kinematics. Okay, so once we start kinematics, I will also be referring you to some additional reference books apart from the module. So in those reference books, we'll be doing questions from kinematics also, and we'll be doing some division questions from calculus if required also. Okay. So that's it for today's session, people. Thanks for attending and wish you all the best.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.